for the moment, to announce the question, the elementary question, we begin with the linear partially hyperbolic automorphism, which is, of course, absolute partially hyperbolic diffeomorphism. And then, for partially hyperbolic automorphism, linear map, this is a linear algebra, that all of the center leaves are the foliation tangent to this bundle. Of course, it exists because it is linear. So in this case, all of the center leaves are either real lines, homomorphic to real line, or they are circle compact. Okay? And they are circle if and only if you have eigenvalue with modulus 1. Okay? Whenever you have 0 upon the exponent, you have compact central leaves. So this is just linear algebra. And then the question, elementary question that we had was the following. Is it possible to find a nonlinear partially hyperbolic diffeomorphism on 3 torus such that its central upon of exponent is 0, but still it has non-compact central leaves? Okay, so it's a very naive question. And at the moment, well, okay, as I announced, this is my talk with the history of a project began some years ago and the outcomes during these 5 years. So this question was not trivial at first, maybe at the first day, at first weeks, and then after some months, with the help of one of my students, well, let me first say to you that by Hammer-Lindell thesis and the Hammer-Lindell result, every partially hyperbolic diffeomorphism on 3 torus is leaf conjugated to its linearization or the action on the homotopy. So if you concentrate on the dynamics of the central leaves, then the dynamics is essentially the same as the linear automorphisms. Okay? By leaf conjugacy, we mean that there is a homeomorphism such that sends the central leaves of nonlinear partially hyperbolic diffeomorphism to the central leaves of the linear guy. Okay? So in particular, they are homeomorphic. Okay? So the central leaves of partially hyperbolic diffeomorphisms on 3 torus are either all of them are circle or all of them are homeomorphic to R. And in the linear case, we know this dichotomy by linear algebra that they are circle if and only if their Lyapunov exponent is 0. So the question is whether the smallest scale behavior of nonlinear diffeomorphism and the largest scale behavior of the nonlinear diffeomorphism can be opposite or not. Okay, is it clear? So this is the question, in fact. This is the elementary question. This is the definition of leaf conjugacy. So by leaf conjugacy, we mean a conjugacy in the foliation terms. Okay, the homeomorphism H sends the central leaves of nonlinear dynamics to the it commutes the central leaves exactly conjugately to the isomorphically as the linear guy does. Okay? Well, in larger scales, I will explain what do I mean by larger scales. In larger scales, the behavior of F, nonlinear guy, and the linear guy are similar. This is just, again, elementary homotopy theory. Okay? By larger scale, similar larger scale behavior, we mean the following. For any k and c, there exists a number m, positive number, real number n, such that if you work on the universal cover on R3, so you can lift everybody, the nonlinear and linear guy, then when you consider 2 points which are far from the behavior of F, the iterates of F and iterates of A behaves similarly. Okay, so you have this. This is just because they are homotopic, in fact. So this means that In the large scale, the behavior of nonlinear and linear guys are similar in the central direction. And the question, the elementary question was that whether this can be the behavior in a small scale. By a small scale, I mean Lyapunov exponent can be opposite. We say opposite because I'm trying to find the example of zero Lyapunov exponent with nonlinear central leaves. This doesn't happen in the linear case. Okay? So with Gabriel Ponce was my PhD student. He is now at Unicampi, another university, state university in São Paulo. We found an example of really center vanishing Lyapunov exponent and non-compact central leaves. So let me announce to you the example, as it is all of these things are really simple to announce. So this is the matrix. So essentially the idea is that you would like to find linear guys, linear partially hyperbolic automorphisms such that the central Lyapunov exponent is very close to zero. Okay? And these guys, for large k, satisfy what you want. The characteristic polynomial of this matrix is this guy, and what is important is that there is a lemma that if k is larger than 4, the eigenvalues of this matrix, the three eigenvalues respectively goes to 0, 1, and infinity. So this is a partial hyperbolic guy. All of them are partial hyperbolic, and when k goes to infinity, we have this good behavior. That central one is going to be really very close to isometry. But more than this, the eigenvectors, in fact, the eigenvectors of these eigenvalues, they are not going to be very random. The eigenvectors are converging also to a unique canonical base. Okay? So why I'm emphasizing on this? Because now the proof of the existence of this example is really a matter of just doing traditional partial hyperbolic perturbations. Here we have a family of partial hyperbolic automorphisms with k, a discrete family, and the central Lyapunov exponent is going to 0. It is in fact negative here. It is going to central Lyapunov exponent is negative and converging to 0. So this lambda c is less than 1, but converging to 1. And now the idea is the following: you perturb these linear guys who has negative Lyapunov exponent to obtain a positive Lyapunov exponent. Okay? So of course the idea naive, and you need to be careful because you should perturb when your k is going to infinity, then maybe your partial hyperbolic diffeomorphism permits you less perturbation to change the Lyapunov exponent. But this doesn't happen just because of the miracle of those matrices. Those matrices are going to, their eigenvectors are going to be more and more dominated. They are going to have more and more angle. So this permits to perturb the linear guys in C1 topology to obtain a nonlinear guy by a Baraviera-Bonatti type perturbation in C1 topology. It is a local perturbation to obtain a positive Lyapunov exponent. And in particular, you will have in the middle, by intermediate value, you have some guy who has 0 Lyapunov exponent, and as this is this perturbation can be done in a one parameter family continuously, then you have 0 Lyapunov exponent and the same central foliation topology. Here you have non-compact central foliation, and therefore the central foliation of this guy also is non-compact. That's it. Okay, so we were happy. Okay, we have answered our questions. It just took us 1 year, and okay. And then and the outcomes are very nice, because then we saw that, okay, this is much more interesting, this guy, because the behavior of the central Lyapunov exponent is really opposite to this one. Okay, and what will be the outcomes that I will say you would know? So the path, in fact, is partially hyperbolic. Okay. Maybe I should emphasize you in this talk you will see a kind of mathematics that began with simple questions without aiming necessarily a great conjecture, but then you go and you go and you go and you see the outcomes, and then someday you find some connection with some other conjectures, and it was really the matter of joy for us, and this is why I am stating here in this important conference. So the central Lyapunov exponents of G is here, is 0, and it has 0 Lyapunov exponent, and the non-compact central is. Okay, done. We got the example, and there exists a question here that I will put for everybody who wants to join to work on these things. Is there such example with absolute continuous central foliation? But this is not known. We don't know if we can construct an example of 0 central Lyapunov exponent such that all of the leaves are non-compact, but the foliation is absolutely continuous. I will explain maybe if we have time about the details, but let me just go a bit further. So this is the curve that we have, and as I said, we have the opposite behavior in the small and large scales. Okay, from now on, whenever I say example, I mean this example. Here is F, okay? The central leaves of F. Here is A, the central leaves of A. And from now on, whenever I say example, or the class of example, I mean linear automorphism which has 2-dimensional unstable and 1-dimensional stable. Okay? In the example I put, it had 2-dimensional stable, but you just change you just take the inverse. This is a bit more convenient for our book. Okay, so here we have negative Lyapunov exponent, and in the central for linear we have expansion. So one of the classical things coming from Frank, Manning, and you know that there is a semi-conjugacy between this non-linear and linear guy. So you have here an anosoph, in fact, automorphism. It is perfectly hyperbolic, but in fact it is anosoph. If you deform it in C0 topology, then you get this guy F, and we know that it is semi-conjugate, so there is a semi-conjugacy between them, and we should understand a bit more what are the points that semi-conjugacy collapse. Where are the points where the semi-conjugacy is not conjugacy? Well, it is also well known that the semi-conjugacy fails to be injective on union of some intervals, just intervals along center foliation. So there are some intervals on the center foliations of nonlinear guy such that after semi-conjugacy they collapse to points. And moreover, we know that H sends, the semi-conjugacy sends the central leaf of F to central leaves of A, and also the strongest stable to a strongest stable foliation of F, the strongest stable foliation of A. Okay? Yeah.
Can you move the bag, please?
No bag.
The bag on the
I was happy that Charles said me that he will not come here, and I was just putting here because he is not, but he can move. So let's go. Here you have. Okay. So let me go now effectively on the structure, geometric structure of this semi-conjugacy in terms of infinitesimal scale dynamical properties. What do I mean by that? Is that for our example, the central Lyapunov exponent for nonlinear guy are negative. Okay, so you have Pessin stable manifolds, central stable manifold. And what happens is that the first thing is that we claim that under semi-conjugacy, Pessin stable manifold inside this center manifold collapse under semi-conjugacy. Okay, the first thing that this guy collapsed, and this is easy to see because of the larger scale similarity between linear and nonlinear. So this is the first claim that the Pessin stable manifold should collapse exactly by the semi-conjugacy. The proof is just this picture. So if suppose that 2 points on the Pessin stable manifold, stable manifold inside center leaf. Suppose that they do not collapse by the semi-conjugacy, so you have an arc which goes to an arc, and then by the semi-conjugacy, and then if you iterate by A, by the linear guy, this arc will expand because you have expansion, but if you iterate by Fn, that arc will shrink, and this is not possible. You cannot have the semi-conjugacy to send this small thing that is large.
Move the table now.
This is just for people who like the jokes and
Maybe we can lift the screen.
and no, I have another problem. I think that it's not a problem. Okay, so then what happens is that, okay, we have this behavior. Larger scale and the smaller scale are different. We have a full Lebesgue measure for nonlinear guy whose Lyapunov exponent, central Lyapunov exponent are negative. So here the atoms comes to the scenario. Now we want to understand the structure of the conditional measure of the Lebesgue measure along central foliation. Okay? So as I said, the collapse intervals, well, I didn't say, the collapse intervals have full Lebesgue measure, okay, which are collapsing on the semi-conjugacy. And we know that the size of the Pessin stable manifolds are uniformly bounded from above. Then, using an argument similar to Ruel and Wilkinson, we can manage to prove that if you consider the disintegration of the Lebesgue measure along these collapse intervals, then the conditional measures are indeed atomic measures, or Dirac measures. This goes back to an idea of Maillet, who announced in ICM, one of ICMs, I don't remember which yet, but yeah, he announced that, okay, if you have a foliation of compact leaves with compact leaves, which is invariant by the dynamics, and the Lyapunov exponent along the tangent bundle of the foliation is positive, then the Lebesgue measure should disintegrate along this foliation singularly with respect to the Lebesgue measure. This is because if you iterate, the leaves should grow, but you can't grow infinitely. This is the same idea. Here we use the same idea for the collapse intervals. So the collapse interval is not a foliation, it is just a partition, measurable partition, and the size are bounded. This is the same as the Maillet's setting, but of course it appears also in where Wilkinson, Wilkinson also results. So what we did with Gabriel Pons and José Regis Varão, who is also in Campinas, we proved that indeed this conditional measure, which are Dirac mass, in principle you may have infinitely many atoms on any center leaf. So recall that we disintegrated Lebesgue measure along the collapse intervals where the semi-conjugacy fails to be injected. But you may have too many collapse intervals, countably many. And what we proved is that, in fact, you can't have more than one. So these are the stable, central stable manifolds, and what we did, in principle it can be finitely many atoms, but we proved that there exists a full Lebesgue measure subset which intersects almost every leaf in a unit point. So this means that the Lebesgue measure disintegrates along central leaves as atomic measure with one atom. So these are the atoms of the Lebesgue measure along the center. Okay? This is called by, well, I like this name. In the paper we announced virtual hyperbolic, but then I'm not very sure that this is a good name. The virtual hyperbolic name appeared in Lindenstrauss and Schmidt paper in an algebraic setting, whenever your disintegration is just atomic, exactly the same. But I didn't see where is the finite index subgroup or something. Nothing algebraically appeared. So maybe my previous name monoatomic, maybe or just. Okay. So let me say you first one of the corollaries of this result. So what was the result? The theorem was the following. Our example, which is positive exponent for linear and negative exponent for nonlinear. This is the example up to the final of the talk. And what we proved is that for the nonlinear guy, the Lebesgue measure, if you see the Lebesgue measure along the central foliation, you just see one Dirac mass. Okay? So there exists this result of Jagan-Yang and Marcelo-Viana. They prove that if you, the same setting, you consider a linear guy which has unstable index 2 and a stable index 1, and suppose that you have an invariant measure for nonlinear guy, ergodic measure, such that the entropy is large enough, is larger than the largest Lyapunov exponent. So what they proved is that in this case, every full measure subset intersects almost every leaf, central leaf, in more than countably many points. So if you have a measure which has sufficiently high entropy for nonlinear guy, then this measure cannot be very, very weak atomic along the central foliation. Okay, this use this Young dimension theory, etc. And what happens is that by our example, the inequality is really optimal. So if you have indeed example where for a nonlinear guy the entropy is equal to logarithm of the is equal to the largest Lyapunov exponent, maybe some battery is failing here. And then you have exactly one atom per leaf. So it contradicts here. So it means that the result is really optimal. You can't have larger or equal. Okay, so this is the picture for the example. So here we have any. So in our example, you can construct the example in such a way that the Lebesgue measure has entropy exactly equal to the largest Lyapunov exponent of the linear guy. Okay, another exponent is negative in our example center, and okay, as I said, the disintegration is atomic, so the result should be really larger and not larger equal. Okay, so let me go a bit more say about the outcomes which was really related topics to dynamics. Well, not exactly these related topics, not as deep as the things that I said in the beginning, but still I think that they are nice because this is a question of geometric measure theory that if you can find a measurable partition which is minimal. So let me just very rapidly say you what is measurable partition. Again, I don't like this name, but still this is the name that Rochlin used and many other people. I myself also use. But measurable partition a bit confusing. But it means that the partition is countably generated. Okay? So let me just put the definition of measurable partition. So if you have, this is a very, very abstract setting, given a partition of Lebesgue space, so you take a partition, any partition, okay, whose members are measurable subsets. Then you can correspond the sigma algebra, which are the saturated subsets by the elements of partition. And there exists a reverse procedure. Whenever you have a sub-sigma algebra of your sigma algebra, then you can generate a partition from this sigma algebra. Don't worry, because I will give an example and we will go rapidly from these definitions. A measurable partition or a countably generated partition has a very nice, beautiful definition. A partition is called measurable partition or countably generated if this procedure is a loop. In fact, if you begin with a partition, you correspond the sigma algebra. And then if you come back to another partition which is related to this sigma algebra, you should come back to the same partition. This is a partition which is measurable. Let me give you a very trivial example. If you consider, you see here, I don't know what to do. if you consider a flow, irrational flow on the torus, on the two torus, then the partition generated by the flow is it is a partition. All of the leaves are very nice, KML, nice, homomorphic to R. And then this partition is minimal in particular. This is a minimal foliation. All of the orbits are dense. And what happens is that if you go to the sigma algebra generated by this partition, you get the trivial sigma algebra. This is the ergodic property of the foliation, this irrational rotation. And then when you come back to the partition, you get the trivial partition. So this is an example of a partition which is not countably generated. You see it in elementary ergodic theory courses. And this shows that this is a good definition for measurable partition, an algebraic definition in fact. And then again, the example, another outcome of our example was an answer to the following question. Is there exists a partition? This is a geometric measure theory question. Can you find a partition or a foliation of a space whose leaves, all of the leaves are dense, so it is minimal, yet it is measurable? So it means that you can separate them in terms of measure theory, but they are minimal. You can't separate them in topological sense. Then, still, we know that measure theory and topology are not the same nature, but still this question was open, and our example yields a question, an answer to this question, because just for simple fact that the conditional measure along the central leaves in the example are just atoms, Dirac mass. The central leaf, central foliation is minimal there in the example, and with respect to the Lebesgue measure, the partition is measurable because it is a partition by point. Okay, partition by point in a manifold is measurable or countably generated. There. Okay, let me go the rest of my time now to most hot dynamical topics. Recently, we used the ideas of this disintegration of the Lebesgue measure along the center of foliation to study this problem of uniqueness of equilibrium states for partially hyperbolic diffeomorphisms. maybe I should apologize to people that had done results on equilibrium states, because probably I have been very selfish and will not refer to the people here, but many people here inside this room have worked on uniqueness of partial hyperbolic diffeomorphisms in different settings. But let me say you what is our context and relate to this integration and these games. So consider a partial hyperbolic diffeomorphism. No, this is not the example. Go out of the example. You consider any partial hyperbolic diffeomorphism on torus which is homotopic to A. Let me just say that this from now on, or even for the result on the atomic disintegration, what is important is not exactly T3. It can be any Tn partial hyperbolic with just one-dimensional central foliation. The point is that one-dimensional central limits. Okay? So consider any partial hyperbolic diffeomorphism homotopic to A, and now we want to understand the equilibrium states for some potentials. Consider any potential, in principle a continuous function, such that the linear guy for this potential has unique equilibrium state, and the equilibrium state has full support. By Bogan result, it is the case for the any Holder potential function. Okay? And then, okay, here we consider a potential for nonlinear guy which is constant on the collapse intervals. So as you see, in the context of equilibrium states, people who work on equilibrium states for partial hyperbolic diffeomorphisms typically work with potentials which are constant along the places which are wrong. And here we are doing also the same thing, but I think that this is the way. You should begin with this case and go. So what is the result is that if you consider any potential which is constant along the fibers of the semi-conjugate C, and any ergodic equilibrium state, well, first of all, there are equilibrium states because it is one-dimensional by results of Gias, Fischer, Pacifico, who is more? I think, as I said, Carlos also, there are many people have worked on this. Yeah. Maybe all of them. Yeah. All of them are here, at least. I don't know. Okay, what is the result? Is that we want to understand the uniqueness, not existence. We obtain a dichotomy. Either the collapse interval has zero measure, okay, and in this case you have unique equilibrium state, or the collapse intervals are full measurable, have full measure, and in this case you have indeed non-uniqueness. You have another, really you have another equilibrium space. Okay? So let me remind you, this is the picture. This is not the example. You have the collapse intervals, and the dichotomy says that either your collapse intervals are nothing, so you have in this case unique, you have some isomorphism with the Anosov guy, or your collapse interval have some mass, and in this case you can really construct another equilibrium state. And the idea is using again this integration and atomic stuff, this kind of thing. So the propaganda for this approach, in fact, okay? Well, what do you do is that we use our result, previous result, in the case of equilibrium states, we announce it for the Lebesgue measure, but you can do it for equilibrium states, and you know that your equilibrium state, the first one, has atomic disintegration. So along central foliation, your measure disintegrate to just Dirac mass, and from this you can construct another equilibrium state, just attaching another atom, which is the boundary of this collapse interval, and then integrate and get, okay, and then take another equilibrium state. Okay, both of these equilibrium states project down to the equilibrium state of the linear guide, and they are different because their conditional measures are different. And as a corollary, we have the following theorem, using again this atomic disintegration theory. The announcement also is very similar to the known results in the theory, but not exactly in this setting, in the partial hyperbolic, with non-compact central leaves. We can prove that if the variation of the potential is small enough, then you have uniqueness of equilibrium states. Okay? In particular, this gives off Raoult-Urey's result because measure of maximal entropy corresponds to the potential equal to 0, which has very small variation. Okay? And maybe another comment about this result is the following. The most irritating comment for the authors is that we do not have example of Holder potential, which satisfies the second.
What is the second item? Sorry.
The second item is non-uniqueness, the most glamorous example. Okay, we don't have the Holder example for that, but using our example, we can obtain continuous. Continuous is not so surprising, but maybe the surprising fact is that we have a continuous. We have a continuous example of potential where the linear guy has unique equilibrium state, but the nonlinear guy has not unique equilibrium state. Okay, for a continuous potential. Okay, what is the example? The example is the example. It's the same example. So what is the example is you consider this guy and the nonlinear guy, and then we know that the Lebesgue measure for the nonlinear guy has atomic disintegration. Okay, so what you do, so here in this case the Lebesgue of collapse interval is 1. So you just push forward your measure by the semi-conjugacy, you obtain a measure for the linear. So whenever you have an invariant measure, then it is a functional analysis argument. For this invariant measure, you can find a continuous function whose unique equilibrium state is that measure. Okay? So if you push forward the Lebesgue measure to the linear setting, then for the linear guy you have a continuous function, and then you consider exactly the potential related to this continuous function. This has the Lebesgue as a unit, as a equilibrium state. This potential has Lebesgue as one of the equilibrium states, but as I said, the Lebesgue disintegrate to atomic measures. And in our theorem with George Chrysostomo, another PhD student, he is in Peru, we prove that if the equilibrium states disintegrate into atomic, in this case, indeed you have another equilibrium state. You have necessarily non-uniqueness. Okay, so here I emphasize that this approach is interesting, although it doesn't give non-uniqueness for Holder potentials, but okay, maybe we didn't work too much, and so on. Another approach. Okay, so the questions. The examples that I gave you are partial hyperbolic, but even for the anosophic pleomorphisms, we don't have central foliation with atomic disintegration. The examples are partial hyperbolic and not anosoph. We don't have example for anosoph diffeomorphisms, where the Lebesgue measure disintegrate into the central foliation in 2 atoms. And also, we do not have examples of ergodic measure with more than 1 atom on central leaves. Not Lebesgue, another measures. These are the things that still I love, because they are really simple to announce, but sometimes difficult. Oh, these are the dream questions. Is it possible? I'm sorry. In fact, no, I did it by proposal. So, because these are not very solid questions. These are the questions for questions.
To avoid pictures.
These are the question for questions. What is the question for questions? It makes sense to put it on the slide. This is why I put them. The question is that, what are the atoms? For instance, you can make your own question. If you are geometric, if you like differential geometry, take the foliation, okay? And you want to understand what are the atoms of this integration of measure. This means that the foliation has a very bad holonomy. It is not absolutely continuous, okay? If the holonomy map is absolutely continuous with respect to the Lebesgue measure, then, okay, so what are the atoms? Are they the point that the curvature of the leaves are, I don't know, critical point of the curvature in the families? I don't know. You should make the question. So one of the questions is it related to the curvature or not? In the algebraic setting, do they mean any number theoretical meaning in the Lindenstrauss and the Schmidt paper? I don't know again. So this is why I put it as question, because these atoms seems some things very strange for me. And another question is that, as I said you, the Lebesgue measure in our example disintegrates into atomic measures, okay? So you consider another measure, sometimes it is called twin measure. You take another atom, and then you construct another measure. So what is another measure? Lebesgue measure is very natural and very, very favorite for all of us, but what about the twin of Lebesgue? Who is the twin, Lebesgue's twin, in fact? Okay, so let me go to more serious. And finally, I would advertise also about our very recent published, very painfully, after 2 years, by Gabriel and Regis also, we pushed too much these arguments of this integration to study these higher hierarchy questions. It's not a good idea to do this kind of juniors should take care. Okay. So the question was, this is a very old question. Whenever the Kolmogorov property implies Bernoulli property. This is another dream that I had. It is 10 years from now, and I have a conjecture. It has lasted 10 years. It doesn't mean necessarily that it is a good or bad conjecture, but it's really I will announce for you about Kolmogorov and Bernoulli property. This is very well-known thing. I thought that maybe I cannot arrive to the end of my talk, and I didn't put much more references here, but there are many people who worked on the equivalence of Kolmogorov and Bernoulli property. And what we did, here I just announced that for partial hyperbolic diffeomorphism, preserving the Lebesgue measure, then if you assume the center unstable absolute continuity of foliation, the Kolmogorov and Bernoulli property are equivalent. In fact, the most pop result would be to announce an example which is Kolmogorov, but it is not Bernoulli. But if you find that some systems which are Kolmogorov, they are Bernoulli, you get the theorem also advanced. So this approach resulted to us also this theorem, and our conjecture is about the example which is Kolmogorov but not Bernoulli in dimension 3. In fact, Katok had constructed in higher dimension very recently Federico Rodriguez-Hertz and Kaligovsky and Von, I think if I pronounced correctly. They announced an example in dimension 4 of diffeomorphism on 4-dimensional manifold which is Kolmogorov. Kolmogorov means any partition, any non-trivial partition has positive entropy. Okay? Bernoulli is the most chaotic thing that you can imagine. they constructed an example which is Kolmogorov, but it is not Bernoulli, but it is in dimension 4. For dimension 3, we conjecture that in 3-dimensional partial hyperbolic diffeomorphisms, the compact central leaves, if you have central Lyapunov exponent equal to 0, and the atomic disintegration along central leaves, and the quotient of the Lebesgue measure is not a product measure. Okay, very, very technical, but maybe this conjecture is mostly for people who know this invariance principles, Avila, Viana, etc. So you have, in 1 minute that I have lasted for me.
You don't have the limit.
Huh? I'm more? You are very kind to me. Okay, so in partial hyperbolic diffeomorphism, in the setting where the central leaves are compact, it's very different to the setting that I announced for you, which were non-compact, which preserve Lebesgue measure, okay, and you have accessibility property, okay. So one of the very nice thing here is that if you quotient the Lebesgue measure with respect to the central foliation, you get a measure here on the quotient space, which is essentially a torus, 2-dimensional torus, and the dynamic is the dynamic Anasov homeomorphism, an Anasov dynamic. And then there is a dichotomy of Avila, Viana, and Wilkinson, who says that this foliation, this central foliation, is either absolutely continuous or not. Well, but it is absolutely when it is absolutely continuous, then you should be rigid. Okay, rigid means that this example essentially is rotation extension of some Anasov difference, and or it is not absolutely continuous. But when it is not absolutely continuous, you can still go and understand the conditional measure of Lebesgue along central foliation. Okay. So what I propose is that if the conditional measures are atomic, okay, and then you can find some cases such that the projection of the Lebesgue measure is not a product measure, not product. In fact, if it is product measure, then these invariance principle arguments began with Ledapie and then for nonlinear case by Avila and Viana says you that okay, you should be rigid, but the point is that we would like to find this example in the setting where the disintegration is atomic, the quotient measure is not product, and the guide, of course, it is Kolmogorov, but it is not Bernoulli. Well, this is another dream. I don't know if it will yield anything, but I hope. It appeared also as a conjecture after we announced. It announced also in the paper of Federico and others, Kanibovsky and Von. I think they put it that Katok had said something, etc., and they put also a conjecture. Okay, I just finished. Thank you. Thank you.
Do you expect to have similar result for central bundle with higher dimension? Because you're using 1 dimension.
Which result? Yes.
About the equilibrium.
Okay, about the equilibrium states, I think I don't have idea, because for the equilibrium state it is really 1 dimensional, the construction that I explained to you. The atomic disintegration, the atomic disintegration can be pushed for the higher dimension under some conditions. But the construction of another equilibrium states uses these intervals and the boundary of the intervals, etc. So maybe you should go. The boundary of the intervals are natural points which are invariant by the dynamics. So this is the unique thing that we use of interval. If you find some natural substitution of invariant subset by the dynamic higher dimension, yeah, okay, but let's see.
Okay, please.
So
maybe a silly question, but are there examples? Are there examples where the entropy is just the biggest Japan exponent and the disintegration is not monatomic? If not, do you expect that your example to be the rule?
It is the zero exponent case, you say, yes?
Yeah.
Yeah, exactly. I don't know. I don't know. If you have example with zero exponent, it is equal exactly, and it is atomic. I don't know. A good question.
Good question. So continue then with the maybe silly question. You have this restriction on the variation of the potential to
Yeah.
get the
Uniqueness.
is that or do you know examples?
Oh no, this is sharp in sense of our competence.
I'm not sure if you're competent, but there are results. Okay, let's answer again. So we will restart in 5 minutes.
Don't forget that at 11 you have
Como chefa que eu quero tirar isso.
Passa a palavra, ok.
O Loreto.
Ele ficou magoado agora.
Agora é o momento de brilhar e a mulher deixava assim.
Não aceita o clamor do teu momento. beber então.
Garrafinha antes de começar.
Well, I have the great pleasure of introducing Big Vito Pinheiro from the Federal University of Bahia. He's going to talk of synchronization of place time. Well, please.
Thank you. Great to be here and.
Oh, louder.
Oh, okay.
Without microphone. Louder without
Okay.
microphone.
So it's louder enough for the people in the back. Yeah. Okay. So I tend to say some few words in the end of the talk about Wellington and this meeting. But right now I prefer to go straight forward in the talk because otherwise maybe the people can hear or not. So, okay. So I'm going to talk about synchronization of place time. Most of you know about hyperbolic times. So place time is almost everyone here know about this lemma, and so this is the title. I'm going to.
Outra série.
Okay. So this, most of this talk is in this paper that I uploaded to the archive recently, and so the framework here is we have X, a metric space, we have a measurable map F, and this set is the power sets of the natural numbers. And we can put a metric. Can put a metric in the power set. This is the natural one, and with this map, the power sets of the natural numbers is indeed a homomorph to the shift of two cycles. So, and this is the homomorph. Okay, so. Sorry again. Okay. So as we are talking about subset of natural number, we have the definition of natural upper density is this one here. Most of you know that. And if this limit here is x, that's this, so we can talk about the natural density of a subset of the natural density. Okay. It's how many element of the subsets appear in when you go to the density. Okay. And so the idea here is the following: when you study a dynamical system, there are many occasions that you don't want to follow all the moments of the dynamic, but in a special moment, a good one, that in that moment you have a good property that you want to use. And so here the idea is you have two collections of good moments. The moments I'm going to call is the schedule. You have some kind of event, and you can make the schedule of events, the times that the subset of natural number that this event occurs in the future for a point. And the question is, if you have two of these events, U and V, for instance, and we want to know how much, or the density of the intersection of these two sets, these two subsets of the natural number. That is, we have two good moments that we select, and we want to know if it's possible to get a lot of intersection between these two good moments. And of course, it's not a big deal if you make some fixed displacement of this moment. For instance, you can translate a bit one of these good moments, but if you translate it in a fixed time, this is not a problem because we are dealing with deterministic dynamical system in many of the usual context. You can follow, you can have a good information if you know in the moment n, if you know the moment n plus l, if this l is fixed. So the kind of problem that I want to talk about here is this one. You have two schedule of events, and you want to know if there is some L, the displacement, and with this fixed displacement, the density of intersection between these two good moments is bigger than zero. Okay, the upper density.
Excuse me, do you permit L to be varying with J but uniformly bounded, or it is universally constant?
No, in this we are going to make L independent of P, for instance, and
J.
no, look, this is the set of J's here that these two moments going to intersect. You can think that L is zero.
Okay.
So
It's bounded. It's bounded.
it's bounded.
No, it's fixed. It's about fixed.
L is fixed.
Fixed.
Yes.
Okay.
Okay. So let me motivate you about this kind of question about this kind of synchronization of good moments. And one of the reasons I begin to start this is the Venus conjecture about the existence of SRT measures. If you almost every point from a smooth map in a compact manifold, we don't have zero Lyapunov exponent. Okay, if almost every point for in M you have only non-zero Lyapunov exponent, Marcelo conjectured that this is a sufficient condition to produce SRB measures. This is a difficult conjecture, and we have here 20 years, and there are no big advances in the direction of proof or disproof this conjecture. So let me recall what is Lyapunov's point, non-zero Lyapunov's point here. Is that we can, okay, in this case we don't have the limit in general does not exist, so we have to choose between lim inf and lim sup, and I think this is the most convenient definition of the X has only non-zero Lyapunov exponent. Okay.
So you are assuming that.
This is a definition. You can put here lim sup, but I think that the more convenient definition is lim inf. Okay, if you put lim sup, better, but.
So F in principle is not non-invertible, right?
Sorry?
You go to plus infinity with n.
Yes.
Yes. It's non-invertible in general.
In general, non-invertible. Let me let me put the non-invariant version of this conjecture. Is this one? You have again a compact manifold, and suppose that your map is simple as alpha, and it's a local diffeomorphism. To simplify, maybe the map can have a critical region, but let me put this frame more simple. And so, suppose that, let me go back here. Yeah, okay. Suppose that Lebesgue almost every point in the manifold, we have only positive Lyapunov exponent. This limits bigger than zero for Lebesgue almost every point. Okay, so Vian's conjecture in this case implies the existence of absolutely continuous invariant measure, in particular SRB matter, okay? Indeed, the contract says that almost every point is going to belong to the base of attraction of one of these. Okay, but this is the non-invertible version of the contract. Okay, and let's fix in this frame, this figure. Okay, and one year after Marcelo published his conjecture, he and José Alves and Cristiano Bonatti changed the condition. They assume not the positive Lyapunov exponent. I'm going to talk about the non-invertible case, okay, now. And so they changed the hypothesis of only positive Lyapunov exponents, that hypothesis here, by this one that most of you know. This is the Newey condition, non-uniform exponent condition, for Lebesgue almost every point. Okay, and with this condition, they prove that the essence of absolutely continuous invariant measure, and indeed almost every point belongs to the base of attraction of one of these measures. Okay. So, what is the difference between this hypothesis, the only positive Lyapunov exponents, and the hypothesis of the ABV paper? Yes. Okay. And what's the difference between the two? I want to show you that the difference is that this hypothesis here imply a synchronization of place-time for associate to the Lyapunov exponent. Okay, let me.
The second hypothesis.
The second one implies the synchronization. So everyone knows here the definition of a co-cycle. I only put here for completeness. So subadditive co-cycle is this one, and the additive and the superadditive. Okay. And okay, to make precise the statement that the difference between the ABV hypothesis and the positive Lyapunov exponent hypothesis is the synchronization of the Lyapunov, the place-time of the Lyapunov exponent. We need to consider our auxiliary map, this Q product here, and we can consider using this Q product. You can see that this map here is indeed additive co-cycle for this auxiliary map. Okay, you can write down here the function and see that it's a additive co-cycle. So here we have
so
not
F is the derivative, is a differential, is a normalized, or it's a differential map at each stage. Big F.
Sorry, F is a differential map. Okay.
F is a differential map.
Yes, and at least C1 map. And so you consider this Q product here only to make this map here being additive co-cycle. So, but here we have not only the point, but also the direction that we are considering. So with this, I'm going to define the place-time. So suppose that you have a co-cycle. I don't care if it's additive or subadditive or any kind of thing. We say that n is okay. Consider some constant. We say that n is a gamma phi place-time for x if we have this for every k between 0 and 1. So you can think the average is good for any k between 0 and n. So this is the picture that you can get in mind. So if n is the place-time, you're going to see from between here and here a good average like that. So I'm saying average because in the case of additive one is indeed average. Okay, only to simplify. So you're going to see a good average here, and you see a good average from here to here, and from here to here, and from here to here. You cannot say anything about the average between two consecutive values, but for the point of the end and all of other points, you're going to see a good average. This is going to be a time for the x with respect to these two, the constant and the time. Okay? So, who knows the hyperbolic time? This is an example of hyperbolic time. Okay, so now suppose that you have a x and the Lyapunov exponent, this limit that represents the Lyapunov exponent, positive. So this limit is bigger than 0, and you can define for x and n vector in the tangent bundle in the complex. Okay, you can let's define this M here as the set of all gamma or half gamma and phi complete times for this one. So this is a subset of the natural numbers that is the all good time associated to x and v. Okay, this type for that. Okay, so the problem is if you fix x and you take two different vectors, v and u, like that, you don't know if this is your hypothesis. You don't know if these two schedule, because this is a schedule of events, these two schedule of events has synchronization.
So Victor, you're assuming that both of those vectors have that Lyapunov exponent.
No, we are assuming that x, all the Lyapunov exponent of x is positive. This implies.
That they're all smaller than gamma. They're all at least gamma.
Yes, sorry. No, because this is gamma. This limit is gamma, so half of gamma they are going to rinse this.
Right.
Okay, so but
that's a minimum.
Yes. So, but you don't know if you can get, you have one direction, the same point, you have one direction and the other direction, don't know if you get a simultaneous place time in these two directions. So this is the problem. That this hypothesis does not imply this synchronization. You need a upper density at least. Okay, it's not only intersection, but okay. So, but if you change your hypothesis, not the hypothesis of all Lyapunov exponent positive, but the hypothesis of ABV is this one. So you can use please lemma to show that you have positive density of place time. Okay, but now we are considering this cocycle, this one. Okay, so now the only thing that is come here is the points, not the direct direction. So the cocycle is this one, and you can consider all the place time for this cocycle here. Okay, and as this cocycle is less than the previous one, let me try to go back of this one. No, sorry. Okay, this cocycle is less than. Let me go back to of this one. Okay. So because of that, you can conclude that indeed, if you use this hypothesis, you are going to get that this collection of place time for this cocycle here is in the intersection of all collection of place time for x and any v in the tangent bundle. So in particular, you can synchronize the place times for in the directional place times in this case, for which the displacement 0 is a good. So for every so this hypothesis implies the synchronization of place time in associated to the a given direction. Okay.
Sorry.
Sorry? You cannot see that? Let me try to do that.
Now we have another reason for complaining.
Okay, let's,
No, but Wilken, so the point is you're saying that all the place times are the same. What do you mean? They're all
okay, because the difference is with that hypothesis, you can consider some direction v and some direction. This is x, so that u, and you consider the place time associated to this direction and the place time associated to this one.
Yes.
So with this hypothesis, the WV hypothesis, you're going to get a synchronization of
But why? I don't understand your argument.
The argument is that this cocycle is less than the cocycle, the directional cocycle. It's a calculation of.
That cocycle is less than the directional
This
cocycle.
is the minimum, no, that is the minimum.
Yes, it's the minimum.
So they all have the same place times, basically.
Yeah, you have a collection of place times that
It works
is
for all
in
of
the
them.
intersection
Right,
of all.
right, it works for all of them.
Yes, and this collection has positive density, and so you
Yeah,
can.
so you get for L equals 0 in this case. You
Yes,
get-
yes. Okay. So let's. So the point is Vienna conjecture is very hard to do something about that, and so the idea is this is a popular Brazilian expression, at least in Bahia, and comer o pirão pela borda means pirão is a very hot and dense kind of soup, and if you try to eat it, you're going to burn. So you try to eat the pirão in the edge of your plate, and so.
Newspaper to help.
So what this means? This means that maybe it's a good idea if you one can become to understand how you can synchronize things, synchronize place time, synchronize this kind of schedule, and with this, if you become to know much about it, maybe you can say something about Vienna's conjecture. Because Vienna conjecture, let me be explicit about this, if you can synchronize the directional place time for a positive set of positive Lebesgue measure, you can use ABV results to conclude the existence of absolutely continuous invariant measure, that's ABV measure. So if you can synchronize place time, you can solve Vienna's conjecture. So let me give you another motivation. Is for me, I was working with Alberto Pino several times about this kind of explosion of differentiability. And the problem is, suppose that you have two maps and they are conjugate, okay? And suppose that the first one has some measure that is a expanded measure. That is Lebesgue almost every point, you have only positive Lyapunov points. Okay? And the problem is, okay, if you have a expanded measure, you can construct a induced map. Okay? Like that. And every induced map, every element go the whole open set, the big one here. And but this map is uniformly expanded one. And this induced map is well adapted to your measure. This means that you can lift your measure to this induced map. I'm going to talk about the list problem in a few minutes, so let me be vague here. Okay, so the problem is, okay, if you have an expanding measure, maybe the push forward of this expanding measure can be also expanding measure. For instance, if you are in one-dimensional dynamics and your expanding measure has positive entropy, so the push forward is going to have also positive entropy. This is going to mean that both measure are expanding measure. Okay, so this is not a very common. So what's the problem here? The problem is, okay, you have the first one. This measure it has a good induced scan, but you have a second one, the push forward of it.
Victor, it's not possible to.
Sorry. The second one. This one also has induced Markov map, expanding map associated to it. But the problem is that this conjugate don't do good things between these two induced map. What we want indeed is that if you try to conjugate, this map here to produce an induced map that is well adapted to the push forward. You are not going to see this. Sorry, here is. You are not going to see that this J map is also a expand one. It has a good distortion and a lot of things. So the problem is there are some way that we produce two induced map, one well adapted for me and the other one for the push forward. That these two induced map are expand and a lot of good properties, and that your homeomorphism conjugate this to one. So this is in interest to to many problems that I'm interested in. But so if you can make a synchronization, because you know you have here, for instance, the way to construct this kind of induced map is using hyperbolic times. But the hyperbolic times associated to the map F. Okay, the two measures are hyperbolic, but you cannot translate the induced time for one map to the other one because this is only a homeomorphism. So this measure in the push forward is going to have hyperbolic times, many hyperbolic times, but the two hyperbolic times cannot, in principle, be synchronized. If you synchronize these two sets of hyperbolic times for the push forward and for the original measure, you can construct two induced maps, good ones, well adapted to each of the measure, and you can try to make a lot of interest.
So that's the main question here.
So,
To get synchronization with the second one.
yes. So this is another motivation, but okay, I would have motivation enough now, and let me. How many time I have?
About 23 minutes.
Okay, let me rush it. So let's go back to the problem. So it's easy to produce a schedule of events that you cannot synchronize. This is a true example here. This is a point of the shift. You can use the only between the shift and the power sets of the natural number to produce two schedule of events that you cannot synchronize. I'm not going to talk. So it's easy to see that there are many a schedule of events that it's impossible to synchronize. But if you see this kind of pattern here, don't look at pattern that appear in if a point is associated to any invariant measure, because you see there are no recurrence here. So the idea is to make a definition and try to synchronize event in the presence of an invariant measure. And we say that an event is coherent if the event satisfies these two conditions. These two conditions obviously is get from the property of please times. Okay, so this second one is you can make a concatenation of good moments. This is the meaning of the second one. And the first one is, in some sense, is very natural. If you are here in time 0, and you're here in time n, this is a good moment. For instance, this is some event that will occur in n time. So if you are here in this one time after, so how many times? So if n is a good time for this, for sure it's a natural hypothesis that n minus 1 will be a good time for u one day. Okay, in the when you pass through one moment. Okay, so this is the kind of hypothesis. So this is a natural hypothesis. It's associated to this time. And let me say that when you have a current schedule of events, that is the event that satisfies the two properties. Okay, so you can consider this kind of induced map, that is the first moment that your event is going to occur here. And this, in this case, for a current schedule of event, you have a very good property for this induced map. Okay. So to try to make the synchronization of current schedule of event, we need, this was our strategy, we become to study this kind of induced map and try to make a good characterization of liftable measures. Let me talk about the lift problem. So suppose that you have a map in a mapped space, a measurable one, and an induced map is a map defined on a subset of this metric space to the metric space that satisfies this kind of formula. Okay, so these are the definitions of an induced map, and a measure, F invariant measure, God, for instance, is F liftable if you can find a invariant probability mu, okay, called the lift of mu, that this one will be capital F invariant probability, and satisfy the condition that the induced time is integrable with respect. So if this occurs, you can show that you can write your original probability like that. Okay. And so this is our first result. So the theorem say that in a very general context, a measurable liftable with respect to a induced map is equivalent to satisfy this other conditions. This one is the same of being listable, only that you have a good bound between the measure of the set and the list measure in the formula. Okay, but let me talk about the two condition. You see, this condition say that be listable means that this is the original, the point of the original order. Okay, this means that the induced order appear with frequency, a good frequency, in the original order. Okay, so you have the original order here, and be liftable is equivalent to say this is the original order. Okay, this point here, and suppose that these one are the induced order. So the induced map do that, and the original one do that. So the important thing is that the density of the induced order in the original order is not zero. The upper density. Okay. So this is a condition, and okay, it's equivalent also to this one. But why this condition is interest? Because indeed, if you get your induced map associated to the first place time of something, okay, so this condition is going by place lemma. This condition is going to be satisfied automatically. So this is this condition you get free for most of the problems that we are going to do. So another point here is we give also a condition for the unicity of this list, of the list, and to the list be ergodic. So this is also interesting in some application. Okay, the condition is the list have to be odd coherent, and odd coherence this condition is very natural. The intersection of two orbs for the original map must be equivalent to the intersection of the two orbs in the induced map. Okay. So I'm not going. I don't have time to be very excited, but you can use this kind of film to produce some kind of field. But I'm not going to talk about it now. And so I'm only stating here the Please lemma. Okay, if we have a superadditive cocycle, have a good density, the Please lemma I show you this. And this, if you have a superadditive cocycle, you can prove that the collection of Please times always produce a coherent schedule effect. Okay, both, but let's go. So what's the strategy here to prove the synchronization? It is to focus on this kind of set. This set is the coherent block of associated to the schedule, and you have to think the coherent blocks was inspired in the Pesin, the hyperbolic blocks of Pesin theory, and also of Armando, the property of the set that survived for the redundancy elimination algorithm of Armando work. So this set is, suppose that you have your schedule of events, the good moments, and you want to know if there is some set that every time that you hint the set, this will be a good moment, that is, and belong to your schedule. Okay? And so, the result is that this is always true, and this set is a big one when you are working with invariant method. So, if you have an invariant method that see with frequency your schedule of event or your event, so you are going to get that the measure of the set is given by the density. So the first thing that if this is true for a measure, you're going to see that the density, the upper density is equal to the density, the limit at least for almost every point, and this is going to be exactly the measure of this hyperbolic, this coherent block. And here is okay. This is the second here on sequence is good to another kind of problem. I'm not going to talk about it now. Okay, so with these results, the primary results, this one, that these coherent blocks are big, you can prove that you can do a synchronization for any collection, finite collection of coherent schedule. You suppose that you have a finite collection of coherent schedule with a positive density of events. Okay, so you can find a finite. You can find a displacement and one and n that we are going to synchronize all this scheduling with a positive density. Okay, and I don't know how.
Talk about let me see, 15 minutes.
Okay, so I'm not going to not now. So you can use these two theorems to prove something like that. You can prove the existence of a good induced time associated to a ergodic expanded measure, for instance, and more than that, you can prove that the lift of these measures. You have a expanded measure. You can construct an induced map with good properties, expanded one, and form expanded one, and well adapted to this measure. This means that you can lift the measure to this induced map. But indeed, you can say more. You can say that the lift of your original map will be this restriction of your measure to a subset. So this is we think to study thermodynamics formally. Okay, so we can also make an extension of Cox's result. So this is okay. With natural conditions, you can also get that the integral of the induced time here is also 1, like the Cox's result. The current time is, in particular, the first return time is always a current induced time. So this is a generalization of the idea of first return map, first return time. Okay, and okay, but let's go back to the other conjecture. What we can do or say about the synchronization of hyperbolic times, directional hyperbolic times associated to positive Lyapunov exponents. So the idea here is suppose that you have only positive Lyapunov exponents. I'm bounded for 0, for instance, here to simplify, and we can define the residual in a point, the Lyapunov residual, as this one. This, you know, so if your point satisfies that, so there are some times that this average here is going to be half of this one. So you take the first time that this occurs here, and this will be induced time, like that. This is the first time that you see half of the expansion that you expect. Okay, and so if you here is your map, you are going to have points. You can split your phase space and subsets associated to the induced time b is some integer, okay? And maybe you have also something like that. This may be infinite, okay? And the residual b0 means that if you take a point, the point is going to go around your phase space when you iterate it, but the time that the point spent in the region with a very, very big induced time goes to 0 in this sense. So the density is going to be 0, like that. Okay. Let me say that if suppose in this context you have already know that you have absolutely continuous variance measure. So in this case, it's easier to use a vivo. Result is easy to conclude that the Lyapunov residual is going to be 0 for almost every point. So the Lyapunov residual being 0 is a necessary condition in this context for you to get absolutely continuous variance measure. So, but you can also prove, using the previous result, that this is a sufficient, not only necessary, but is a sufficient condition also to get the existence of absolute continuous variance measure. And the strategy to prove this is, okay, you have a point, and you look for the set of accumulate. You have a point x, that you have a positive Lyapunov exponent. You look for the set of accumulated points of this in the probability space, the invariant probability space. You look all the accumulation points of this, and you can call this, for instance, this. This is all the accumulated points of the point of this sequence. And so, you're going to have that this is all measure here is going to be an invariant measure, probability, and the idea, okay, here you can synchronize things because the previous result. So the idea is to use the hypothesis of the residual being 0 to translate information to this set, and here you can synchronize things and push back the information for the order of x, proving that indeed x satisfies the ABV property, that is the x has you can synchronize all the directional please time for x. So with this you can prove this.
So you can have examples without with the residue is non-zero.
Okay, only this kind of not good example. Example that you built in a formal way to. I don't have a big class of example. Only
you have any example?
Sorry.
You have an example.
Example, but it's a very constructive. Is only one example. It's not a big class. It's not a good one in this sense.
Well, but you have an example where the
yes.
is positive and the residue is non-zero.
Only one example. Yeah, but it's I don't like the example because it's anyway. So what the idea here is to try to begin to get information about synchronization and understand how you can use the kind of information.
No, but the idea is you don't expect to have a big class of examples of that, right? I mean,
no, but an open class, for instance, the hypothesis of ABV, you can give an open class of map that you get the yes.
No, I'm talking about examples where this fails, so you don't expect to have a large class of examples with the residue.
No, the problem here is the following. If you try when you try to get make an example, the example almost every time is in the class of ABV. It's direct in the class of ABV. You have to give an example that is not clear. ABV example. So this is the problem.
Different thing.
So you're talking about examples where the residue is zero or examples where the residue is non-zero?
Example that you have the residue is zero.
No, I want the example where the residue is
On the
non-zero.
contrary.
The contrary. Okay. Non-zero. No. Non-zero. But if I had an example with non-zero, this is equivalent. So the Viana's conjecture is false.
Right, exactly.
So no, I don't have this. No, I don't. I don't have it. I think that Viana conjecture is true. I don't have this kind of thing. So, okay, let me. Sorry. Maybe, Chairman, maybe you can ask if there are some questions or comments.
Apparently, the talk by Clayton is finished. Now, question, simple question. Please don't let me ask. Please.
Regarding to Stefan's, but I think you answered, but it is not obvious. It is your result. So you claim that Viana's conjecture is equivalent to have synchronization for limit almost every point?
Yes. If you have a synchronization, you can put almost every point going to satisfy ABC condition.
And if it is true,
yes,
necessarily should have, because you have an invariant measure.
Question, then we come again. Milton. Please, Milton, continue.
So I hope that this meeting is not an unusual one. I think that this meeting is associated to a person that was very important for many of people here, and also from Brazilian and South American and anything, dynamical school. And I want to say some words about Wellington, but I want also to ask people, for instance, there are some people here that's going to give a talk, but the other person in this room may also give some few words about your experience with Wellington. So I have the pleasure that Wellington was my professor in IMPA, but also become a friend. And we shared. He was a very tough guy, and he was as was told a professor that most of the students was afraid of him. But ironically, this was not my case, because every time that when I was a student, I tried to talk to Wellington. He was okay, a hard one, but he always say, okay, tell me what you think. I'm going to give you some time to explain to me with what you think. And this for me was amazing, because and he indeed pay attention, and so I cannot be afraid for someone that you can discuss with him, that you can argue with him, and he's going to listen. So sometimes he proved that I was wrong, and sometimes he told me, okay, you are right. So that was, for me, was very interesting because besides of he looked like a very hard one, but indeed he was I cannot say sweet one, but a very fair one. And yes. So for me it was hard that I was in the hospital in the day before he died, and he was very happy. There he make a lot of jokes about, for instance, he told me, people say that I don't have a heart. See? And he was in that moment very happy, and I left the hospital so happy also, because I was there to think that, okay. And in the political opinion was almost in the opposite direction of Wellington. But again, this was very interesting because we talk a lot about politics. I give him my opinion, and if he has some good points to say, you are not correct, he say something, but most of the time he's going to his house 2-3 days after he's write to me, okay, now I have a good argument to and we chat a lot about it, and I visited his house, and we traveled together, and I want Google. I was very touched by Google. It's not in a good shape, but he told to the doctor on Saturday that he cannot. He has to come here because this meeting is about a very a friend and a colleague and someone that he respects a lot. And so, Google, maybe you're not going to give a talk, so maybe say something about Wellington if you want.
Very difficult.
Google, come here to the front, please.
Vamos lá.
Muito bem. Well, first, difficult to say more about Wellington, but many people told about Wellington. Wellington was a very good friend of mine, of course. I also like it very much to discuss politics with Wellington. My political opinion, perhaps even more distance. But I went many times to Angra with him, and he was a very good friend, besides being a top mathematician. He was my first PhD professor in dynamics. I did hyperbolic dynamics with him. As Wilton said, most people was afraid of him, so the class was formed by myself and by Steve. Anyhow, we learned a lot of mathematics. It was a great course, and yeah, so he also teach me a lot on hyperbolic geometry. I was not formally a student of him with human surfaces, but he liked very much the subject. I learned a lot with him, many things. He never convinced me of his political positions, but he convinced me about many of a lot of his mathematical ideology. So deep influence not only on me but in the whole our whole school of dynamical systems. So really a great guy.
Let me say something. The good thing is that in political terms, Wellington was always wrong. But about the students.
So he was a reference.
About the students, most of the students were afraid from Wellington because one of the things that Wellington always said was, that is trivial.
Yeah, that's in my book.
And then I remember one day, many years ago, when the old cafe of IMPA worked, that Jacob was discussing with Wellington about, I don't remember something, and then Jacob, Wellington told you, that is trivial. And then Jacob said, oh, but that is your easy test. I don't know if you remember or not, but it's that like this. Well, I need to stop here because I consider I was a good friend of Wellington, and then I don't know if someone else want to say something. Then let us again. Well.